Okay, let's talk about circular motion. So, the simplest kind of circular motion is when an object moves in a circle at a constant speed. And a good approximation to that is the Earth going around the Sun or the Moon going around the Earth. It could be a runner or a car running or driving around a track at a constant speed. So even though the speed isn't changing, the object's accelerating. So circular motion is always, under all circumstances, there's an acceleration, accelerated motion. And we know that if an object is moving in a straight line and a force is applied in the direction of motion, that it speeds up. And if a force is applied opposite the motion, it slows down. But if a force is applied perpendicular to the motion, then think about your components. There is no component of the force in the direction of motion, so it doesn't speed up, and there's no component of the force opposite the motion. So this week we're just going to look at simple, uniform circular motion where the object doesn't speed up or slow down. But you can imagine if we applied a force, say, this way, there would be a component in the direction of motion which would make it speed up, and a component this way which would make it slow down. So that would be an object moving in a circle and speeding up. And if we applied a force this way, that would be an object moving in a circle while it's slowing down. But this week we're only going to look at this situation. And in the case of this situation, since there's no change in speed, right, acceleration is defined as the change in velocity over the change in time, which is v final minus v initial. But if the magnitude of the velocity isn't changing, only the direction is changing, watch what happens. So here's the velocity vector here, and a little bit later here's the velocity vector. So if we take v final like a vector, and we take v initial and we make it negative, it would be this way, then you see that v final minus v initial is this vector. Now because of the way I drew it, it doesn't come out exactly right, but you see the vector, the acceleration vector, is pointing toward the center. So in the case of centripetal acceleration, acceleration where the object is not speeding up or slowing down, we calculate, without deriving it, I'll give you the equation, we calculate the velocity, we calculate the acceleration by taking the speed, the magnitude of the velocity squared, and dividing it by the radius of the circle. So this is the only new equation that we have. And we call this centripetal acceleration because it is acceleration which always points toward the center. So notice as the Earth goes around the Sun, the force of gravity is always pointing toward the center. So the force is constant in magnitude, but always changing in direction. And the acceleration is always toward the center, the direction of the force. So one more thing. So if we take the Earth and we take the Moon, and the Moon were stationary, it would fall to the Earth. But since the Moon is moving, why doesn't it fall to the Earth? The answer is it does fall to the Earth. The Moon wants to move this way, but falls to the Earth. And now the Moon is trying to move this way, but it falls to the Earth. So as it goes in a circle, we could say it's constantly falling to the earth. Okay, the last thing before we begin doing problems is all the problems this week and last week, and as we continue throughout the semester, often, since they're force problems, they often start with this equation. So someone asked me the other day, what's the equation for the normal force? Well, there is no equation for the normal force. So how do we find the normal force? Well, we find the normal force, say, by using this, by using Newton's second law. And in some cases, the normal force will be equal to mg. But in some cases, we see the normal force is equal to mg cosine theta. And there are a whole variety of situations. So almost all of the problems we're doing this week, and we'll continue to use this, starts using Newton's second law. And when we use it, we never use it in this form. We always use it either this way, or both ways. Okay, now I'm going to start doing the MOPs. So we're doing the Minds on Physics. CG, circular motion and gravity, 1 through 5. And in section 1, there's a set of questions where you have a circle and a point, and you're given the direction of motion, and you're asked to find the vector. So that's always tangent to the circle. So you should know this from your math. Tangent to the circle is a line that touches the circle only at one point. And if you draw a line and touch a circle only at one point, it has to be tangent to the circle. So as this goes around, the tangent to the circle is this way. And you can picture this if you're moving around a track. At this instant, you're moving in this direction. And if the force, if the string broke or the gravitational force went away, you'd move in a straight line. And so if the direction were changed, so it were this way, the tangent would be in the opposite direction. And so no matter where you are, you draw the tangent to the circle, and that's the direction of motion, right? The tangent line. And one of the things that you may know from circles is that the tangent line, if drawn properly, is always perpendicular to the radius. So the force is toward the center, the motion is always perpendicular to the motion, and that's important because if it weren't, the speed would be changing, but only the velocity changes. So remember what we said earlier. If a force is in the direction of motion, it speeds up. If it's opposite the motion, it slows down. If it's exactly perpendicular to the motion, it doesn't change the speed, only the direction. So another set of questions involve objects on a string traveling in a circle. So as these things travel in a circle, right? They're all spinning at the same rate, but their velocities are different. So this travels in the same time, less distance, so this velocity is less, this is greater, this is greater, this is the greatest velocity, or speed, I should say, because the velocity is changing. And that's because the velocity depends on the radius. So the last type of question in CG1, the first section, is they give you a series of circles, different radius, different radii, and different period. Period is the time it takes to go the circumference. And so you're asked to rank the speed. So pause the video and try and do that. And if you're not sure, I'll explain. So the speed is distance over time. distance it travels, and the distance it travels is 2 pi r, the circumference, divided by the time it takes to go a complete circle. So all of these are going to have 2 pi r, so we can ignore the 2 pi because it's in all of them. And so we simply need to divide the radius by the time. And so for this one, for A, we get 1. For B, we get 1/2. For C, we get 2 divided by 1/2, which is 4. And then for D, we get 1 divided by 1/2, which is 2. So C is the fastest, goes the longest distance in the least amount of time. D is next, A, and then B is the slowest because it goes the shorter distance in a longer period of time. Okay, I looked over CG2, and it seems like we've discussed most of what you need to know to answer those questions. So when an object moves in a circle, its velocity is always tangent to the circle, if it's moving this way, right? But the acceleration is always toward the center, always perpendicular to the velocity. And since centripetal acceleration is given by v squared over r, it should be clear that increasing v will increase the acceleration, and decreasing r increases the acceleration, because we say this is an inverse relationship. And the acceleration does not depend on mass, right? It only depends on the speed and the radius. So CG3 talks about centripetal force and inertia, and there are many familiar examples. So here's one where you're driving the exit ramp off of a highway at a reasonable speed, maybe 40 miles an hour, and the exit ramp is quite curved, and you hit a patch of ice. So when you hit the ice going in this direction, your car goes off the road. And so we often describe that as being thrown off the road, but actually what's happening is you're just following your path in a straight line because there's no longer friction with the road, because in order to negotiate this circle, you have to have a friction force with the road that keeps you in the circle. And if you lose that friction force, your natural inertial tendency is to go in a straight line. So a better way to say it would be that as you do the circle, friction is pushing you toward the center of the circle, and if friction goes away and there's no longer a centripetal force, there'll no longer be a centripetal acceleration, and you will go in a straight line at a constant speed. And the same way, if you're a passenger in the car and the car's turning, it turns in a sharp circle, going fast in a sharp circle, then the friction of the seat may not be enough to move you in that circle. So what happens is you tend to go in a straight line, and the car comes and the side of the car pushes you in. So you're not being thrown against the door of the car. The door of the car is being thrown against you. In other words, as you tend to go straight and the car turns, the car meets you and pushes you toward the center of the circle. Another example I think that's not mentioned would be a washing machine. And so as it spins faster and faster, the centripetal acceleration gets bigger, and it's the wall of the washing machine or the amusement park ride that's pushing you toward the center. So the person in the ride or the article of clothes wants to go in a straight line, but the spinning machine comes and pushes the article of clothes toward the center, and if it's going very fast, that pushing force can be very great. And so it's important to realize that when you're moving in a circle, there is an unbalanced force. This is something that you'll forget. the centripetal force is not balanced because you do get an acceleration when you're moving in a circle. So it's easy to get these questions wrong if you're not careful. So CG4 is a series of questions that will prepare you to be able to do CG5, the calculation problems. So here's one of the first problems that shows up in CG5, and so let's do it. Okay, here's the data given, a 1,100 kilogram car on a level roadway moving at 18.5 meters per second, and the radius of curvature of the roadway is 43.5 meters. So this is moving in a circle, right? And we're looking at it at this point in the horizontal circle where it's coming towards us. So it's a three-dimensional problem. The car is kind of coming out of the screen at us. The normal force is straight up, the gravity force is down, and the friction force is the centripetal force. So notice this is unbalanced in the x direction. So the sum of the forces in the x direction are not zero. And the sum of the forces in the y direction are zero because MAY is zero. And so from that, because of this, we can say that F norm equals Fg. That's not always true, but in this case it's true. And to get the net force is the sum of the forces in the x direction equal to the mass times the acceleration in the x direction. And so for this case, there's only one force in the x direction, the force of friction. And that's equal to the mass times the acceleration in the x direction, which is a centripetal acceleration, v squared over r. Okay, so do the problem, fill in those blanks, and then come back. Okay, check how you did. So what did I do? Well, I started with the grav force, since that's the easiest, just mg. And notice the MOPS would probably have you put the whole number in. But if I ask you this question, this problem should have three significant figures. And this number, right, it's not 9 rounds to 10. So this number would be, if we're following the rules of significant figures, which generally I ask, you would put in here 1,100. And then the normal force, of course, is equal to, because of the sum of the forces in the y direction being 0, is equal to that. And again, depending on the MOPS or depending on a question that I would give you, you would write the appropriate number here. For me, it would be 11,000, not 1,100, excuse me, 11,000. Now, then you go to the friction force, and your natural reaction is going to be, oh, friction coefficient times the normal force. We've done that many times, but then you look at the problem and there's no coefficient of friction. So you say, oh, I don't know how to calculate the friction force. Well, in physics, we often use the equation to calculate, or we get it indirectly. So in this case, the friction is actually the last thing we're going to get, and we get it by using this equation. The sum of the forces in the x direction equal max. We can find ax, the centripetal acceleration, because we have the v squared and the r. So if I take v squared over r, I get this number. But if I'm doing 3 sig figs, it's going to be 7.56. But then when I calculate the net force, I don't use the rounded number. I use this number times the mass to get the net force, mass times acceleration. So notice, sometimes we get the net force and then get the acceleration. Here we have the acceleration, and we use the mass to get the net force. Then you need to recognize, oh, the net force is the friction force. So this number to 3 significant figures would round to 8,460 newtons. That's the number that goes in here. Okay, here's the next type of problem that I see showing up on my sheet. We have the amusement park ride. The object is spinning rapidly. And so we're given the mass of the person. We're given the diameter of the cylinder and the time it takes, the so-called period, the time it takes to go 1 revolution. We use a capital T because that's the period. And in the MOPS, these two diagrams are combined, but I like to keep the diagram and the free body diagram separate, so I pulled the person out, and I showed the normal force, right? Interesting, a normal force that's horizontal. Why? Because the wall is perpendicular, and normal force is perpendicular to the wall. So in this case, the normal force is the horizontal force, and it is the centripetal force. It's the force that keeps the person moving in a circle. And if the person's not sliding up or down, then these two forces have to be equal. So when we look at the sum of the forces in the y direction, we recognize that there's no y acceleration. And so the friction force, which is keeping you from sliding, has to equal the gravity force because they have to be 0. But in the x direction, the normal force is the accelerating force, and that's all there is. There's no other force this way, right? This is accelerated motion. It is unbalanced in the x direction. There is only one force that will be equal to the mass times the acceleration, and the acceleration is v squared over r. So go ahead and fill in the 6 blanks and then come back. Okay, here are the numbers I got. Keep in mind that it's always possible that I can make an error, and it's hard to correct the video. So if you see something that looks wrong, email me. So I started with FG because that's easy. And I put the 3 significant figures but kept the bigger number. And for reasons that there's no acceleration in the y direction, these two forces have to be equal. So I can write 730, I left the units out, that should be there, but it's in the MOP, newtons. And then I have all the information I need to get the velocity, right? The velocity is the distance, pi times the diameter, or 2 pi r since we're given the diameter. That's the circumference, and that's the time it takes to go through the circumference. So this is what I got for the velocity by doing pi times d divided by the period. And I put it 3 significant figures but kept the extra digits. And then keep in mind, just like in terms of getting this done, you have this number on your calculator, so don't erase it. Just take the number, that whole full number's on the calculator, square it, divide by the radius. Okay, in this case you do have to take half of that. And get this number. And once you have the acceleration, now you're set up to get the net force. So don't erase the number. Leave it there with all the digits. And just multiply by the mass and get this number. And to 4 digits, this would round to 1591, but we only want 3 digits. So it's 1590 newtons. And once again, that is the only force in the x direction. And so the normal force has to be 1590.76. Okay, I'm going to add another question, and that's what coefficient of friction is necessary for this to work? So see if you can come up with the coefficient of friction. Of course, higher coefficient is okay, but if the coefficient is too low, the person's going to slide down the wall, right? So we have something with a high coefficient of friction, like a rough sort of padding rug, so that you get good coefficient of friction, good stickiness. So see if you can get that. All right, things have gotten a little crowded, but I'm up here. The force of friction is the coefficient. I put static friction times the normal force. But the force of friction is also equal to mg. Of course, we have either one. And so I didn't do the algebra, but the mu is going to be the force of friction or the mg divided by the normal force. So this force divided by this force, and it gives me 0.45896, rounded to 3 digits, 0.459. Hopefully by now you've gotten used to the coefficients of friction. This is a pretty high one. Generally it's 0.2 or 0.3. Low friction would be 0.1 or lower. Friction rarely gets higher than about 0.5. So this requires a pretty sticky surface for this to work. And remember, if this is too low, the force of friction will not be able to balance gravity and the person will accelerate down the wall. Okay, here's the one where the person swings a bucket of water on the end of a rope in a horizontal circle. And so this is our diagram. This is the free body diagram. The tension force along the string has two components. Well, there's two forces, the tension force and gravity. But the tension force has to do two things. It has to keep the bucket from falling, and it has to pull it toward the center of the circle to keep it moving in a circle. So the x component is the centripetal force, and the y component balances gravity. And so doing our usual sum of the forces x equals max, we get that ftx equals max equals m v squared over r for this problem. And the sum of the force is y. Because the bucket is staying in a horizontal circle, isn't accelerating, that equals 0. And so what does that mean? That means that Fty has to equal mg. And think about the physics, right? We're not doing mathematics, we're doing physics. So as this bucket swings around, if the bucket were heavier, it will tend to go down, right? And going down means the y component gets bigger to support the weight. If the water is removed from the bucket and it's light, the circle will be higher. We'll need less y component in order to get the necessary acceleration force, and so the bucket will change angles. Okay, so here's the information: the mass, number of revolutions, time for 10 revolutions, the radius of the circle. Calculate these quantities, and notice that changing them up a little bit, I added the tension force and the angle at which it's swinging. So pause the video and do as much of that as you are able. Okay, lots of calculations. Let's hope I got them all right. So the method is what's important anyway. So since we have the mass, we simply multiply that by 9.8 and we get the grav force. And I'm using the convention of 3 significant figures because that's the numbers we're given are 3 significant figures. So I'm reporting this, but I'm using the bigger number in the calculation. And once again, some of the forces in the y direction are 0. So the y component of the tension force has to be the same. So I can fill that out. And then I get the velocity by the usual equation, but we have 10 revolutions. So I'm going to go, we have the radius, so 2 pi r is one circumference, and I can divide that by 0.763, 1/10 of this, or I can multiply the circumference by 10 and divide by the 7.63 seconds. Either way, this is the velocity I got to 3 sig figs and the larger number. And then, saving myself time, I just leave this on the calculator and square it. Divide by the radius, v squared over r, and I get the acceleration. And so this should, if you're paying attention to the physics, right away you should say, whoa, 62.7. That's a lot bigger than 9.8. It's more than 6 times bigger. So it means the centripetal acceleration is really high. So if you were sitting in the bucket, you would be experiencing more than 6 G's of force as you went around, right? Like that. So anyway, that's useful to recognize. And then when you multiply the acceleration times the mass to get the ftx, which is the net force, right? The ftx equals the net force. You get 109. So once again, looking at the physics, if you're holding the bucket, the tension in the rope would be 17.1, but as you're swinging it around fast in the circle, this tension goes up by more than 6 times to, well, this is the x component. Then to find the tension force, okay, it's just vectors, don't forget. You have the x and the y, so you square the x, you square the y, you add them together, you take the square root, and you get 110 newtons. Since most of the force is the x component, the tension doesn't change much because of the y part. And then once again, what's the angle? That's simple, vectors. We know the y component, we know the x component. So what did I do here? I took the inverse tan, usual practice, right? Inverse tan of the y component over the x component. And that's where I got the 15.2 degrees. So this would be a good problem for the midterm exam. Okay, let's do another. Okay, I see this video this video is getting pretty long, so there's 3 more types of problems. Let's look at the 3, discuss the 3, and then work out the details of one of them just to end the video. And of course, this video is available, so you can come to any part of it whenever you want. You don't have to watch the whole thing at once. So we have the bucket going in the circle, a vertical circle instead of a horizontal circle. We have the plane flying in a circle. And we have the roller coaster car or something going over a circular mound. And so what we want is we want to draw the free body diagrams for all of those situations. So let me take out these lines. Whoops. And so for the bucket at the top, both the tension force and the gravity force are down. And at the bottom, the tension force is up, and the gravity force, the mg, is down. And similarly here, there's the force of gravity down. And if the force of gravity isn't enough to provide the centripetal acceleration, then there'll be like a net air force, airplane force. And here, gravity is down, so the only thing keeping the plane from falling is the airplane force. But if it's moving in a circle, that airplane air force must be bigger than mg. Just like here, if you were holding the bucket steady, the tension force would equal mg. But since it's moving in a circle, it needs to be a net force up. And so the net force up has to be bigger. And this is a little different. So this is on a track. So now we have an mg down and the normal force up. And if the cart's sitting at the top, stationary, these would be equal. But since it's moving in a circle, there has to be a net force down. And so the normal force has to be less than the gravitational force. Now think about the situation in both cases. If you're going over the hill slowly, the net force is small and the normal force will be almost equal to mg. But the faster you go, the more downward acceleration you need, and the smaller and smaller the normal force gets until at some speed you're going fast enough that it's only gravity causing you to stay in the circle. Supposing you go faster. Now gravity's not enough force to make you bend in that circle at that speed, and so that's when you leave the road, you go off the road. So the faster and faster you drive, this gets smaller and smaller to zero, and after zero, the car leaves the road. Speed bumps works that way too. In the case of the plane, at the bottom, this force has to be bigger. And so the faster you fly, the smaller the radius of the circle, and the faster you fly, the more this force has to grow. And as this force gets big, your feeling is that you're being pressed against the seat. You're feeling more than just the normal force of gravity. You're feeling this additional force. And so that's how pilots subject themselves to high G forces. However, when you're at the top, if you go fast, you can use the plane to provide the extra force to make the circle. But as you go slower and slower, this force shrinks to zero. And if you go slow enough, then the gravity force will pull you down. So you've got to be going fast enough to complete the circle. There's a minimum speed at which you'll complete the circle. And the same thing with the bucket. You can rotate it as fast as you want, and the tension force will just get bigger and bigger. But as you go slower, the tension force gets less and less until you're just matching the force of gravity. And at that point, you just complete the circle. If you go any slower, what's happening is the bucket's going to fall. It's not going to complete the circle. At the bottom, no problem. If you go very fast, the tension force just gets bigger and bigger. And if you go slow, it just shrinks to the point where it equals Fg. So there's that variety of situations. I think I'll do the bucket problem. Okay, here's the information. And let's do it for the top and the bottom. So that's the mass of the bucket, that's the radius of the circle, and that's the speed at which it's moving. So calculate all these values and find V min. At what velocity, what's the minimum velocity that will complete the circle and not fall? And just a hint on that. The hint is when the tension force, just at the point the tension force reaches zero and the force of gravity is the accelerating force, the acceleration needs to match that force. What does that mean? That means that the centripetal acceleration must be 9.8 meters per second squared. If it's less, it'll fall. And then at the bottom, do the same thing with these same numbers. Of course, at the bottom there is no V min. Okay, almost done. So at the top, the first thing I did was get the mg. Left the units out, but that's newtons. And then, since we have the velocity and the radius, I calculated the acceleration. This was actually 17.9 something, rounded to 18. And then once I have the acceleration, I multiply that by the mass to get the net force. And both vectors are down. So this plus this equals that. And so the Ft, I subtract the Fg from the net force, and I get this. And just to make sure we did the right thing, I look, and if I add this to this, they're working together, I get this force. This, of course, is negative, but I'm just giving the magnitude. Okay, and the F min is this way. If the only accelerating force is mg, then mg, as this shrinks to 0, mg has to match the acceleration. That's the v min squared over r. That minimum speed doesn't depend on the mass. And so when I solve it, I get that v min is simply the square root of gr. That will be true for any situation like this. And when I take the square root of 9.8 times the r, I get 3.01 meters per second. Then when I go to the bottom, since I haven't changed any of this, I have the same acceleration and the same net force, only this has to be up, and the force of gravity is still the same, 17.052, down. So the net force is the tension force minus the force of gravity. So the tension force will be the net force plus mg. And so if I take the net force and I add the mg, I get the tension force. And just to think about the physics, is this right? Well, yes, the tension force is doing two things. It's holding the bucket up, so it's supplying this, plus it's accelerating the bucket in the circle. So these two should add together to give me 48.4 newtons. Okay, long video. Good luck. And we spent a lot of time on this. This didn't show up on quiz 6, so you can be quite certain that there'll be a good piece of this on the midterm exam. So if you watched all this video and practiced, you should be ready. Well, ready for the circular motion part. Don't forget all the other stuff. And so study the MOPs, look over the labs and the questions that you had on the quizzes, and you should be well prepared for Friday.